In this video, I just want to outline a basic approach for solving the sort of problem sets that you're going to encounter in this course. And the main idea is that when you approach these problems, when you approach these thermodynamics problems, you need to be systematic. You need to approach them in the same way every time as possible so that you don't need to waste time thinking about what to do. You already know what the next step is. Okay? And so when you're approaching these problems, you're basically just going to follow the same 7 steps over and over. So the first step is you got to read the problem statement. Specifically, you need to gather information by carefully reading the problem statement. Okay? More importantly, you need to figure out what exactly the problem is asking you to solve for. Whether it's asking you to solve for pressure, temperature, or some sort of change in internal energy, whatever it's asking you to solve for, you need to identify that first. Determine what problem is asking you to solve for. Okay? And as you're reading, you should also identify any important, properties or quantities. Properties, quantities, or even qualities of the system that will aid you in your analysis. Right? And so as you've seen in MEB1, MEB2, and as you're going to see in all of your other chemical engineering courses, these sorts of properties include things like flow rates, temperature, pressure, volume, whether the system is adiabatic or it's well insulated or it's isothermal. Depending on what the system is, there's a lot of different possibilities. But with practice, you'll be able to identify when those pieces of information show up. All right, so after just gathering information, the second thing you should do is you should pick a system to analyze and draw a schematic of that system. And I stress it's very important to be able to draw a schematic of the system because that will tell you if you actually understand what is going on physically in the system. And so by drawing the system out, that'll help you determine if you have a closed or an open system, so whether there is mass crossing the system boundaries. And as you're drawing the system, what you got to anticipate is that you're going to start writing out some sort of balances. So you're going to write balances. And so those will be mass, energy, and once we get to chapter 4, also entropy balances as well. Alright, so once you've drawn out your system and you have a decent idea of what's going on, and you've also identified what information you know, what you need to start doing now is you need to count out the number of unknowns that you have. And the reason for that is because the number of unknowns you have in your system for your problem, that's going to be equal to the number of equations you need to develop or derive to solve the problem. Right? And so this will help guide you by counting the number of unknowns. It tells you, how hard you need to work in order to solve the problem. Okay? Once you count out the number of unknowns you have, at this point comes a very important step. And this step is when you start listing out the assumptions you're going to make in order to simplify your analysis. So you got to start listing your assumptions, the approximations, and also I'll add on to here, you should also start listing out the reference conditions for each species in your system. Okay? And so some examples of this, some common examples are, let's say your system is at steady state. And so what that is going to mean mathematically is that in your energy balance, your dE dt term is going to be equal to 0. All right? Or let's say that you're told your system is adiabatic. And so what that means is that the Q dot in your system is going to be equal to 0. All right, and so based on, step 4 is intimately tied to step 1, where you got to figure out, what are the qualities of my system and how can I translate those qualities into math. All right, and so that's why it's very important in order to, systematically list out your assumptions so that you know how you could actually simplify the math out in your balances. And so that's it with regards to the assumptions. For the reference conditions, just like you learned in MEB2, there's no absolute value of internal energy or enthalpy. And so we usually, when we calculate those, we're usually calculating a change in internal energy or an entropy. And so in order to calculate that change, we need to have some sort of reference internal energy that we use. All right? And that reference internal energy we're going to set equal to 0. And typically, to do that, we typically set the inlet or initial conditions of our system as the reference conditions. So we use those conditions to set the reference temperature, reference pressure, and reference phases for each of the species in the system. So by convenience, we're just going to use the inlet or initial conditions. All right, and so once you list out all your assumptions and once you list out what you're going to use for your reference conditions, step 5 is when you need to start applying your different sorts of balance equations. So at this point, write down appropriate form of balance equations. And so specifically, these include your mass or mole balances, your energy balance, which comes from the first law of thermodynamics, and then in chapter 4, you're going to learn how to develop an entropy balance. And this comes from the second law of thermodynamics. All right, so write down all the different forms of your balance equations. And in those balance equations, you'll probably have things like volume, pressure, and temperature. A lot of the times, a priori, you won't be told, what the pressure is of the system, or you'll be told the pressure, but not necessarily the volume or the temperature. You won't be told all the conditions of the system. And so in order to gain more information about your system, what you got to do is you then need to combine your balance equations from step 5 with actual thermodynamic models. And so what I mean by that, there are many examples of thermodynamic models. And so some examples include, your pressure, volume, temperature equations of state. So equations that relate those three properties together. And the one that you're most familiar with is the ideal gas law. Other things include heat capacities or heat capacity equations. And also, other pieces of information or models that you could be using are charts and tables that provide the relationships between things like pressure, volume, and temperature. And perhaps the example you're most familiar with from MEB2 are the steam tables. So those are going to be making quite an appearance in this course. All right, and so once you combine your balance equations with the thermodynamic models, at that point, you have everything you need. And so what you got to do then is just solve for all of your unknowns and find the piece of information that the problem is asking for. All right? And so if you follow these 7 steps, this should give you a nice game plan on approaching all of the problems that you'll encounter in this course.